In this video, we're going to take a look at how to characterize this 10.5 gigahertz pulse Doppler radar using a real-time spectrum analyzer. Okay, with the real-time spectrum display centered at 10.5 gigahertz, we can see the instantaneous spectrum of this signal when I pull the trigger on the radar gun. And we can see a number of interesting features here. We can see a couple of different spectral lines in the instantaneous spectrum of this thing that tells us that there's some interesting things going on with the pulse characteristics of this radar. So let's go take a look at some of the pulse characteristics here. We'll open up a time overview window, which allows me to control how much time I want to record and what I want to go analyze. I'm going to set up a simple little RF power trigger at about minus 40 dBm. Now I can see the leading edge of the pulse coming in here. Let's just increase the amount of time that I capture here, and now I can actually see there's a single pulse that I'm capturing in the analyzer. So we'll bring up a few other displays to take a look at what's going on. Let's start off by adding the spectrum and spectrogram displays. And I'm going to simply pause or stop the analyzer here and take a look at what we have. Now by adjusting the time per division scale on the spectrogram, we can do some overlapped FFT processing to see what's going on in the frequency domain over time across this pulse. If I add a marker, I can yank the spectrums out of the spectrogram and show them to you down here as the red trace. And you'll also see where I am in the time domain with the marker over here in my amplitude versus time view. So we can actually see that when the pulse is just starting to turn on, the spectrum takes on this shape that's kind of shown in the yellow trace, kind of overlapped there now. That kind of corresponds to this characteristic in the real-time display. As we walk through the pulse in time, we can see that once we get into the middle of the pulse, we just see that we're sitting at a constant center frequency here. And then as we get to the end of the pulse, we can see that we get another different characteristic shape to the spectrum. And that corresponds to this kind of outline in the real-time display. So we can see that the pulse characteristics, particularly during the rising and falling edges, are what are giving rise to these different characteristics that we see in the instantaneous real-time spectrum. In fact, this shape of the spectrum during the rising and falling edges suggests there's a lot of energy at the lower, below the center frequency during those edges, which tells me there's probably a bit of unintended chirp on this waveform. So if we bring up, say, a frequency versus time display, I'll replay the existing data through that display and zoom in on this display here. We can actually see that as that pulse is coming up in amplitude, we're kind of at full amplitude, even right here, the pulse has not quite reached center frequency yet. And it's only until we get about a third of the way through the pulse where we've kind of settled out in frequency. And we can see when the pulse then goes to turn off, the frequency again falls. So we saw that in the spectrum, and we can see that essentially in the frequency deviation versus time view of the same pulse. Now something else that's clear, when I first pull the trigger, if we look down on the real-time display, you can very carefully see that when I first pull the trigger, some of the initial pulses are coming up at a slightly higher frequency, and then it settles out to be about in the center of the spectrum display. We can see that kind of occurring in the spectrum display here, and we can also see it in the frequency versus time view. But if we capture some more pulses over time, let's grab, say, 3 milliseconds worth of data. If I first pull the trigger, and again zoom in a little bit vertically here again, you can kind of see that characteristic in the frequency deviation versus time, where those first pulses are slightly higher in frequency, and then it works its way down again. Now that we've taken a look at the basic vector signal properties of this signal, such as the spectrums over time, frequency deviation over time, amplitude deviation over time, let's take a look at some more quantitative measurements of the pulse characteristics. Alright, so we'll reconfigure some of the displays I have up here. I'm going to turn off the DPX and frequency versus time spectrum and spectrogram displays and bring up some of the pulse analysis. Let's bring up the pulse statistics, pulse table, and pulse trace to start with. These displays are going to show us some more quantitative measurements that we can make on this pulse signal. We'll start off by looking at this pulse table. The pulse table will show me measured parameters on the pulses that we captured. I've got a row for every one of the pulses I've captured, in this case 24 pulses, and a little over 30 columns worth of data. So simple scalar properties like pulse width, rise time, fall time, average power, repetition interval, and also vector properties like frequency and phase deviation within pulses, frequency and phase deviation from pulse to pulse, etc. We can look at this data a number of different ways. For example, this pulse trace display down here can show you any selected measurement on any selected pulse. For example, let's say I'm looking at the pulse width of pulse number 5. If I click on that cell, I can actually see the pulse width measurement made on pulse number 5. I can walk my way up and down the pulse table and look at the pulse width measurements on individual pulses. I can see which pulse I'm looking at in the time overview display as well as in the pulse table. I can also pick a different measured parameter if I wanted to look at, say, the rise time measurement of a pulse, or maybe the ripple measurement of a pulse. I can pick those measurements and then walk my way up and down the table for any of those particular measurements. We've changed the analysis length now to 10 milliseconds, and let's do a single capture of that. The pulse statistics window can show you any column of measured data versus pulse number, or can show you as a time trend to look for time varying characteristics in that measured parameter. It can also show you a histogram of that measured data, and even show you an FFT of any column of results. And that might help you find deterministic or parametric variations in a measured parameter. Now, while the analyzer can capture a few seconds worth of data, you may need to have statistics over a much longer time period. You can adjust the time period in or out by simply adjusting the amount of analysis length that we have here. But you can also build cumulative statistics over a very long time period. And what we can do is bring up a couple of additional displays like a cumulative histogram and a cumulative statistics display. And these will just continue to build the results over time. So you can let this run and literally gather characteristics over hundreds of thousands or even millions of pulses. I will give you those cumulative statistics in a histogram form as well as in a table. And again, you can pick whichever measured parameter you want and build all the statistics are being characterized for every single one of these parameters. So it's just a matter of picking and choosing what you want to have. The cumulative statistics will build a histogram whose limits are based on measurements from the first 10,000 pulses that are captured, and then after that we'll simply populate the outliers counters here for anything that lands outside of the limits established by the first 10,000 pulses that were measured. Now I've let the cumulative statistics build up here for almost 3,500 pulses that we've captured, but this is doing it one pulse at a time. The cumulative statistics as well as the instantaneous statistics will work with long acquisitions as well. So if I collect a much longer set of acquisitions here, now essentially I've got my pulse statistics plot will show me the characteristics for a seamless acquisition, while the cumulative statistics continue to build results from all the prior acquisitions. So real-time spectrum and signal analyzers can provide a lot of detailed information, both quantitatively and qualitatively, about pulsed RF characteristics, such as this inexpensive pulse Doppler radar gun that we used in this example.
Find out more at Vicom's website.